Okay, so now we have the problem. So when do we use it? So here what we want to go ahead and look for whenever we want to use central limit theorem, the key word that we want to look for is mean weight. That's what we want to look at for mean weight or mean height or anything that associates with mean in front of our variable. That's when we know we have to use the central limit theorem. Okay, so let's first start off with this problem. So it says the weights of kittens is normally distributed with a population mean of 5.6 and a population standard deviation of 3.2 pounds. Okay. So we have kittens, all possible kittens have a mean of 5.6 and their standard deviation is 3.2. So we obtain 15 kittens, right, and measure their weights and calculate their mean. So I can take 15 different kittens, right, and I can weigh them, and then I calculate a 1 grand total mean. Okay, now let's look at part A and figure out what they're asking for us. So this says, what is the probability that a randomly selected kitten has a weight greater than 7.2 pounds? Is there anywhere in there that says mean weight? Well, no, it just says a randomly selected kitten has a weight greater than 7.2. Right? So that's all it says, something that's greater than 7.2, right? So let's go back. So you will have your PowerPoint with you, but let's go here. And this is what we have. We have that our weight of kittens, this is going to be the weight, is normally distributed with a mean, a population mean of 5.6 and a standard deviation of 7.2. All this question is asking us to do is to, let's say I got a random kitten, right? And all I just got, and their weight was what? What was it? We wanted a weight of greater than 7.2, right? That's what we want, greater than 7.2, okay? So if I go back here, right, to my written portion, right? So we want everything that's greater than 7.2. Okay, so let me draw a picture. So basically, there's nothing about means. There's no central limit theorem here, right? So we have our graph. Here's our graph. The mean of this is 5.6, so we know that this is normally distributed. 5.6 is right here, right? Standard deviation is 3.2, and we want everything that's greater than 7.2. Well, 7.2 is a little bit higher than that, right? So let's say this is 7.2, and we want everything that's greater than that. So we're looking for this shaded area. This is just a recap of normal distribution because we know how to do this. This is just very, very simple, right? Because all we got to do is just use normal CDF. So we go into our calculator and we write normal CDF starts at 7.2, ends towards positive 1 million or whatever you want to call it, right? Then the mean of it is going to be 5.6 and the standard deviation is going to be 3.2. So let's figure out what this value is. So I'm going to go ahead and go into my calculator, right? So I have both calculators here. Since most of you guys have this calculator, I'll go ahead and use this one. So I'm going to go ahead and use my calculator, right? I'm going to press second data, right? I'm going to go to distributions, normal CDF. I'm going to put in the mean. The mean is 5.6. My standard deviation is going to be 3.2. Okay. Then my lower bound is going to be 7.2, right? And my upper bound is going to be, I'm going to leave it like that. So when I calculate it, what am I going to get? The probability is approximately rounded 4 decimal places, 0.3085. That's what we get. So the probability of me randomly selecting a kitten from this population, right, that and their weight is greater than 7.2 is going to be approximately 30%. Okay, that's what I got. Okay, it's kind of heavy kitten. Okay, so now let's go back. So this was part A, right? That's what part A was saying, greater than 7.2. Now, if we go to part B, what are they asking us to do? Part B says, what is the probability that the mean weight of the kittens, so the 15 kittens that we got, that their mean weight will be greater than 7.2? This is very different than this problem. Here, we just wanted one kitten was greater than 7.2. Here we want the mean weight of these 15 kittens to be greater than 7.2. This is a central limit theorem problem. Okay, so central limit theorem problem, remember that we want, so part B, this is a central limit theorem problem because the key word that we had was mean and weight, right? Mean weight was the key word. Now, you're not going to see weight all the time. You might see some other variable, but in this case, it was weight, okay? So notice, we want exactly the same thing. We want to figure out the mean weight, so x bar, this is each individual weight, this is now the mean of the weight, and according to central limit theorem, this is normally distributed with a mean mu and a standard error of sigma over square root of n. Okay, now, can we use the central limit theorem here? Okay, well, let's figure it out. Okay, is it normally distributed? Yes, it is. We knew that it was normally distributed. Even though n is much less than 25, it's normally distributed and we can use it. Okay, so we can. Now, all we got to do is just figure out what these numbers are. Okay, the mean is in this case 5.6. So that didn't change. Our standard error, sigma, well, this is 3.2 divided by the square root of whatever this was, which is 15. Okay, that's what we got. All right, so let's calculate this. X bar is normally distributed with a mean of 5.6 and a standard deviation. Okay, so let's put this in our calculator. 3.2 divided by the square root of 15. And I get approximately 0.8262. So let's round it to 4 decimal places. Okay, approximately that. Okay, so now this is now the new information that I'm going to use to solve this problem. So the problem said mean weight is now greater than 7.2. So now we're going to use this new information to figure out this problem. Okay, so what am I going to get? Okay, so we get the mean is still 5.6, right? This is optional. You don't need to do it. It helps me. And then 7.2 is still here, right? It's still the same exact area. Same area. Okay, but now what we're going to do, when we use normal CDF, we are going to change everything is going to be the same except this part, the standard error, because we incorporate the 15, the fact that we got the 15 kittens, right? So we still have 7.2 all the way to positive 1 million or whatever it is, right? Then mean is still 5.6, and now my standard deviation or my standard error is going to be 0.8262. Okay, so let's figure out this probability. Okay, so now let's use this calculator. Okay. Okay, so I'm going to use second vars, go down to normal CDF, then 7.2, comma 1000, a whole bunch of zeros, 5.6, and then 0.8262. Okay, and then I press enter, and what I'm going to get is 0.026 approximately. So about 2%. So the probability of you getting 15 kittens, from the 15 kittens that you obtained, right? The probability that you get a mean weight greater than 7.2 is going to be very, very small. Okay, not very small, not very high. Okay, so now let's do part C, our last problem. Okay, so now what we want, what is the probability that the mean weight, okay, so notice, look, mean weight, so that means that we have to use CLT again, of the kittens will be less than 4 pounds. Okay, so now let's go back. So we want less than 4 pounds now. So mean is still the same, 5.6, and we want it to be less than 4 pounds. So here's 4. Everything less than 4 is over here. Here's everything less than 4. So now what we need to figure out when we use normal CDF is, okay, what do we want? Do we want this one, right? This one? Or do we want this one? Well, since we look, the key word in this case was mean weight, so we don't want this one. This is the regular one from the population. We want the one that we calculated. This one. This is the one that we want. So we want normal CDF, because the keyword was still mean weight. Normal CDF, the mean, I'm so sorry. It starts from negative 1,000, this one, or negative 1 million, whatever you want to call it, right? All the way to 4. The mean is now 5.6, and the standard deviation is still, or the standard error, 0.8262. Okay, so now let's plug this in. If you're still having trouble trying to identify where is the 1,000, the negative 1,000, you need to go back to the videos of normal distribution, right? Because you need to be able to do this that part at this point. Okay. Okay, so here's what we have. Okay, second quit. Okay, so now I'm going to put second data. Go to distributions, normal CDF. Okay, I'm going to click on the mean, which is still the same, 5.6. The standard deviation has now changed, 0.8262. Okay, then we're going to go all the way from negative 1 million. Okay, we're going to leave that like that. And then this is going to change to a 4. Okay, and what do I get? Approximately 0.026. Okay, very similar to this problem. Okay, interesting. Okay, just a couple significant figures off. Okay, I'm going to write it a 4 at the end. Okay, so very similar. Okay, and it kind of makes sense that it was kind of similar, right? Because, no, it didn't make sense, right? Okay, but that's what we got. We got 0.6 for some reason. Okay, but we still got exactly the same thing. Okay. Okay, so yeah, so these were the two, or the one answer that I got in this case. Okay. All right, so what you need to really be careful with is just try to figure out what is initially the original population, right? So what is that? Sometimes they may give it to you, sometimes they may not give it to you, right? And also keep in mind when we use the central limit theorem, right? We use CLT when the keyword in the problem is what is the probability that you see the word mean, right? So we see this. What is the probability that the mean wage or the mean height or the mean IQ is whatever, right? So that's where we go ahead and get it, okay? All right, so I'm going to stop it right now.